Hi there, everyone. My name is Jay Metz. I am the chair of the Ultra Ethernet Consortium, and I'm here today to talk to you about, the Ultra Ethernet Consortium. Primarily, we're going to be talking about networking in the age of AI and HPC, and some of the things that have been going on with this. I'm pretty sure you've heard about AI and HPC recently. It's been kind of in the news once or twice. And since as of this recording, we are about to ready to launch our 1.0 specification in the next few weeks, and I wanted to give a little bit of an update as to what we've been doing so far, and help you understand a little bit more about what we're looking at trying to accomplish and why we're doing what we're doing. So the Ultra Ethernet Consortium has been around since November of 2023. We now have over 120 member companies, and we have about 1,500 individual contributing members. And so as a result, these are very active companies and groups that are working specifically to try to solve the networking dilemmas that happen as a result of these new workloads. Both of these different types of profiles wind up causing a lot of new and interesting problems inside of Ethernet networks. So what we're looking to do and what we're looking to accomplish is make sure that we can scale to really large systems that allow us the ability to be able to handle up to about 1 million endpoints and not lose the efficiency or maybe even gain some of the efficiency. Try to be able to use the backbone of Ethernet, which everybody is familiar with, to create an excellent, reliable network that is demanding for these types of workloads. Now, I think one of the things that's actually kind of important to note is that when we talk about these workloads and we talk about these networks, we're not really talking about your typical bog standard network, right? We're not talking about the kind of network that you'd have in your home Wi-Fi or even in your data center where you've got multiple tenants and running thousands of programs. Instead, we're talking about a specific dedicated program specifically for AI and HPC types of workloads. They're dedicated networks that have very specific needs, and we're going to try to address those needs. We're not attempting to replace traditional Ethernet. We're not even attempting to replace other types of networks. What we're looking to do is try to combine the efficiency of Ethernet, the ubiquity of the cottage industry that goes along with Ethernet, as well as the scalability that we can use based upon these types of technologies, and stand on the shoulders of giants, as I like to say, to be able to tune the network to solve these kinds of problems. So let's talk a little bit about what the issue really is and what we're trying to solve. Well, when you start to look at the AI workloads, an AI workload actually isn't just one workload. It's multiple steps that have to be very precise at particular points in time, and they have very different requirements. So to simply say that I need to have a network that can do really fast communication back and forth is not quite enough. The problem is that we have a need for better memory, right? Memory management, memory communication, and that memory has to be talked to across, well, from a server's perspective, larger distances than just across a motherboard. The other problem that we have to deal with is we have to deal with ever increasing memory capacity requirements. So when we talk about accelerators, like the TPUs, the GPUs, and those kinds of processing capabilities, we want to be able to handle the workload inside of the memory, but that memory is limited. So you have to be able to swap back and forth between these different types of processors that allows us the ability to effectively expand the memory footprint for the workload by using multiple accelerators and their required memory. Now, what that means is that if you start to increase the size of this memory footprint and you have to link them together through some sort of networking capability, that adds additional latency. That's a problem. We want to make sure that we have effectively near instantaneous data access so that we don't wind up with idle processors. This is one of the big problems that we're trying to solve. And if you've got to send part of the workloads from one accelerator to another accelerator, that distance of time and time is one of those things that we have to pay attention to. And it's becoming a more and more difficult problem to solve as these models start to get really large. So even we're talking about large language models, but those aren't the only types of networks that we're really looking at. There's the generative neural networks. There's the other kinds of AI workloads that have to go on. They each have specific types types of processes that have to happen, and those processes have to be communicated across that network. So that's what we're trying to accomplish. It winds up being a rather ambitious approach to solving this problem as you start to think about all the different types of things that could happen inside of the life cycle of an AI or HPC workload. So the communication patterns are not the same for every step along the way. Now, if you start to think about what AI, just to use AI as an example here, what you think about AI is like you take your raw data, you bring it into a system where you have to prepare that data because if you've got all of the data sitting inside of a set of hard drives, and you can't just bring them in and just drop them into a GPU. GPUs don't know how to handle object storage or file storage. You have to convert that into a way that allows us the ability to do the processing. That means preparation. What does preparation mean? Well, preparation means you may have to sometimes decompress it. You may have to sometimes decrypt it. You may have to do some sort of mutation to the data before it can ever be used inside of the workload. That data prep means that there's a bit of work that has to get done. Then you actually get into the data training itself, and there's a forward pass and a backward pass to try to make it validate, right? So cycling through that data is what we have to be able to do, and that data has to move from one location to the other. And then once we're all done, we put this into an archive, or we send it off for inferencing, where we can actually do some of the generative work that you would actually wind up seeing when you start to type into your Chat GPT prompt, right? All that stuff that comes up at that point in time is that the end result of this process. Now, it's a pretty straightforward flow. It makes a lot of sense. You go from raw data through these different steps, and eventually you wind up with your answer on Chat GPT. No problem. Except in reality, it's a lot more complex. In the truth of the matter, the AI workload is actually multiple steps that involve multiple workloads at specific given points in time. Now, each of these different processors, whether it be a CPU or a DPU or a TPU, all of these different things happen to be used at different times. And then at various stages along the way, you have to double check to make sure that it's going okay. Right. So each of these different roles that are played have a specific thing that has to be done at a specific point in time, which means that the entire complexity of the situation is considerably more involved than people may realize at first glance. Now, once we start to get into these really large systems, for instance, the propeller spins the other way. I don't have a beanie hat at the moment, and even if I did, I wouldn't wear it. But if I did, the propeller would spin the other way in this regard. So as we start to increase the amount of communication links between these different devices, we get a logarithmic extension and expansion of the relationships in these networks. And that means we have to be even more careful. We have to account for when things go wrong. And that happens a lot more often than people really realize in these kinds of systems. So the network has to be a robust network, a reliable network, and that's one of the reasons why Ethernet has such a promise in this regard. There's a long history of work being done or having been done inside of Ethernet to allow us the opportunity to be able to solve these problems. So what are the problems that we have to solve? Well, we've got the memory bandwidth that I told you about before, but then we also have to deal with the capacity and the latency issue. If you're trying to communicate with all these different systems, then you're going to have to deal with the time it takes to move from one to the other. And we have certain budgets that we can take into account, and those budgets are unforgiving. So we have to be very careful about what the trade-offs are with the memory, for instance. What about the computation bound workloads? Well, if you're going to be doing generative AI or transformative AI and you're looking at the summarization part of the AI, they have different needs and they have different workload types from the processing perspective. Sometimes you need to have work done inside of the CPU, inside of the OS, inside of that kernel, and sometimes you want to use it inside of a GPU or a TPU, and sometimes you can even do some of this processing in an accelerator on a network card like a DPU or a SmartNIC. All of these different things have different roles, and you have to be able to communicate between them efficiently and effectively. Well, if what happens if you got to a problem? What are the things that can break or at least kind of hurt for a while? Well, you need to make sure that the memory gets into the right place at the right time and in the right order. You have to make sure that you can understand that the network itself can communicate with itself so that you can understand if something goes wrong. If there's congestion, you have to be able to tell the different endpoints that this is happening. You have to be able to recover from problems that are going on. And as we get into these really large systems, it becomes more and more difficult to be able to handle this in a timely fashion. So the last thing that we have to deal with is what happens when you have a problem and it amplifies over time. So everything from the physical layer, where you can get a resend of a bit going across the wire, that takes extra power, it takes extra cooling, it takes extra time, and then that amplifies over time. That can get into congestion, that can get into problems with the workloads not being able to handle, and you're always waiting for that last bit back. All of these things work in concert, and we need to make sure that that concert isn't just a detuned orchestra trying to tune up. And then last but not least, you've got the issues of security. If you don't have very large men with very large guns, you want to make sure that the network itself can be protected. You want to have the possibility of encryption, and you want to be able to make sure that it's part built into the system, because that is something that is quite important for a lot of different companies and people. So these are the problems that we want to try to solve. And what Ultra Ethernet has tried to do is not necessarily replace the familiar Ethernet model, but instead we want to tune the model. We want to tune that stack so that the workloads can have the hardware alignment for the most efficient networking possible. And so for this reason, we've created the concept of the profiles for both the AI and the HPC that address a number of the use cases within these environments. And as we've seen, as you can see on this particular slide, we've got a number of different optional features. In this particular case, they're in sort of a beige color. And we've got a couple of mandatory features, particularly in the transport layer where the magic winds up happening. So as we go up and down the different stack, and we can see all the different projects that we've got inside of Ultra Ethernet at each of these different stacks, the idea is that they're going to be aligned per the profile for AI or HPC to allow us the opportunity to have a properly tuned network. So as you've been able to see, Ultra Ethernet spent a great deal of time examining this stack and searching for ways to tune for these very demanding workloads. So let's go ahead and take a look at them in turn. So at the very top of the stack, we've got the APIs, the application, the software layer. So modern applications use libfabric APIs for mapping into the underlying hardware infrastructure. And so Ultra Ethernet spent a great deal of time integrating these libraries into the software layer. Applications using libfabric exchange messages over the fabrics, over the fabric, and place those messages directly into another buffer's memory. Now, Ultra Ethernet collaborates with the libfabric community to extend the libfabric API as appropriate and necessary. And it's an ongoing project that is going to continue to work long after the 1.0 specification comes out. And here we go. Okay, so in Ultra Ethernet, the golden ticket, so to speak, is it happens in the transport layer. This is the area that is the only real mandatory element inside of Ultra Ethernet. There's a lot of other optional things that can help tweak and tune, but this is the only thing that we actually consider at the moment to be mandatory. The Ultra Ethernet transport, or UET, is designed to separate out the semantics of the transport packets from the delivery mechanism while including the optional built-in security mechanisms. So the semantic layer is designed to integrate with AI frameworks and HPC libraries through that libfabric mapping that I told you about. So this is also the place where the reliability assurances and the congestion control take place. So the packet delivery sublayer, or PDS, it determines the selection of the appropriate services for the correct semantics. So different applications are optimized for the various reliability and packet ordering constraints. So the PDS then provides the protocol with the multiple modes of operation that offers all combinations of reliable, unreliable, ordered, unordered packet delivery services. Yeah, and there we go. So one of the things that we wanted to do at Ultra Ethernet was ensure that security was a first-class citizen and not just an afterthought. So the Ultra Ethernet transport incorporates network security by design and can encrypt and authenticate all network traffic sent between computation endpoints. And UET offers a new key management system and the new mechanisms that allow for efficient sharing of keys among large numbers of compute nodes that participate in a job, but it doesn't require ballooning the session state. So in the host and the network interfaces, they can maintain a low footprint for this based upon the way that the packet delivery system is identified. I have to use a relatively awkward presentation for today, so forgive me. All right, so And one of the things that we've said for a long time at Ultra Ethernet is that we don't want to rewrite the protocol stack. And on the contrary, we just simply want to stand on the shoulders of giants, and we only want to tune in the places where they make the most sense. So one of those places could be inside the switches, where when congestion occurs. So for that reason, we have the ability to optionally use trimming. Now, trimming is when packets are marked in transit. And that's what happens when it recognizes congestion signals in the network from the endpoints. And that allows the switches to truncate the contested packets. Ugh, say that 4 times fast. Now, the way that it works is that it modifies the DSCP field in the truncated packet headers and then forwards it to the destination, as the congested signal. Now, what that does is it allows us to provide a lot more information about the congestion that's going on than just a simple ECN bit by themselves. And that way it allows the endpoint to be able to resend just the packet that's necessary for the drop truncated signal. And it makes it much more efficient, much more streamlined, and a lot less traffic being sent across the wire in a congested and contested environment. So this is one of the major advantages that we have as an optional feature for the network. Okay, so this is the basic comparison slide about what we're trying to do versus what traditionally has to be done and why we think it's probably the best way to go about doing it. So one of the things that we're trying to do is make the network, more efficient as it scales. Now, another way to think of it is this way. The farther along you go inside of a network where there are more and more endpoints, the more inefficient the network becomes. Right? There are a lot more systems that have to be put into play to make sure that the reliability works, and those wind up burdening the network, and you effectively don't get to use the entire system as it evolves. In fact, the more bandwidth you throw at it, the worse it gets too. So this involves a number of interconnected technologies that increases the efficiency while at the same time makes it more intelligent for handling the unpredictable patterns that can cause problems like congestion. So one of the ways that we do this is with packet spraying. Now, with the Ultra Ethernet transport, every flow may simultaneously use all the different paths to the destination, as opposed to having to create, blocked paths for efficiency's sake. Now, this creates a balanced use of all the network paths, and we can avoid the load imbalances, and by using a coordinated choice of the paths through the fabrics between the endpoints and the switches. And this is guided by real-time congestion management. It's a fine-grained load balancing, and it results in a better network usage and reduced tail latency. Now, we also allow for flexible ordering, and that allows applications to have workload-specific requirements for messages and packet ordering that, in turn, directs the appropriate transport services, like I was talking about earlier with the packet delivery system and the semantic layers. So the UET is innovative because it couples the multipathing, the flexible ordering, and the congestion control to use direct data placement on a per packet basis without requiring a reordering buffer on the destination side. So one of the side effects of extremely large networks is the unique traffic patterns that emerge. And these require significant improvements in congestion handling, especially as the speed and feeds of accelerators increase. So Ultra Ethernet uses coordinated congestion control over multiple paths between endpoints, and that's flexible whenever some traffic is sprayed and some is not. So these methods can reduce incast and allow for faster response time, even as those networks continue to grow in size. Last but certainly not least is the true nature of the ambition of Ultra Ethernet. We recognize at the very beginning that while the largest networks are only currently reach into the tens of thousands, maybe even the low hundreds of thousands of endpoints, this is a temporary situation. What qualifies as an endpoint is going to become far more fluid than just a network card inside of a server. You're going to find ports and fabric endpoints on the accelerators themselves. It could be a DPU, it could be a GPU, it could be other types of accelerators somewhere inside of the system. But the network itself that's going to be doing this is not necessarily, if you pardon the pun, hard coded as it currently stands, and it's going to be far more flexible. So from the very beginning, we decided that we were going to try to look for solutions that had at least 1 million endpoints and without having to rewrite from scratch. We didn't want to just do this work and then have to redo it all over again in a couple of years. So the way that we've really started to address this, and the first thing that we've been tackling is the ability to create efficiency and reliability at scale. That is the big thing, is that when we start talking about these large systems, you have to be able to have a network that's going to handle it natively, and that's what we've been looking to do. In the future, it sounds almost like the Disney ride. In the future, um, we're still working on a number of extra projects. So as I mentioned before, this is an incredibly ambitious project. It requires multiple eyes on the prize, and so the implications for these modifications to the Ethernet stack have consequences that go far beyond the protocol itself. And so these consequences include storage, management, performance, compliance, and large groups of people doing large amounts of work, including major partnerships with other industry associations. So this is a big deal. And so UEC is going to be continuing the work in these areas, and they heavily depend upon the proper networking constructs in large scale environments. So additionally, we're going to be looking at further enhancements. And we're going to be tuning those kinds of workloads. So, for instance, getting into large systems means improving the telemetry aspect, as well as exploring the potential for facilitating workloads inside the network, such as collectives, right? All to all reduce, that kind of stuff. Now, beyond that, we're looking at even more long-term projects. Can we create more fluid congestion control? Can we handle some of the more advanced topologies that are common in HPC and becoming more common in AI? Things like Dragonfly, Tori, Megafly, and so on and so forth. What about distance? What about physical distance? If you want to be able to have like a metro level kind of a thing, or campus approaches to these kinds of networks. All of these topics are ripe for consideration at UEC. So as you can see, we've been busy. We've been very busy working out the layouts of the foundation, and we've got to be able to handle these demanding workloads, and they're only going to get more demanding over time. And there are many moving parts. So if you wish to find out more, and we're going to be providing an awful lot more information, including some training materials and some more educational materials as well. I do think you might want to head over to find us on the interwebs, right, at ultraethernet.org. And we'll have several of the upcoming key networking conferences throughout the year where we'll be participating and going into even further detail about how each of these different systems will work. So thank you very much for your time. My name is Jay Metz, and I'm very happy to have had the opportunity to share this with you.